Great to see you here again. We have the last video in the part related to the applications of congruences. In this part, I will talk about check digits. Now, check digits are very important because they offer us the possibility to verify a sequence of numbers, and we can verify if the sequence that we have received, if it is correct, yes or no. Now, when we look at the importance of check digits, there are a lot of applications like barcodes, account numbers, for example, like bank and other accounts, ISBN numbers for books, binary strings, money orders, airline tickets, and of course, many other applications can be found, is where we are using strings to create unique identifiers. And when we have those applications and we link a unique identifier, a unique string to them, we have to be sure that the string that we are transmitting or the string that we received is a correct string. Did something happen in the transfer? Did somebody try to change something? That's also a possibility. So we have to see what is basically happening. Now, we have to find, or we can define special rules to identify possible errors in the different strings. And the method we are using is by adding a check digit at the end of the number. So basically we have a set of numbers plus one additional number. The first set of numbers, except the last one, is in fact the identification of the product of the book. The check digit is added there to verify if that number complies with a specific rule. And depending on the application, the rules change. We look at the congruences and modular arithmetic, and we use those to verify that the string of numbers is correct. So it's a direct application of congruences and modular arithmetic. There are different systems that exist. We have a system which is looking at the value of bit strings, the parity check. We look at the numbers for products, which we know from barcodes on products. They have different rules that they are following. And then we have typically, for example, the ISBN numbers that we use. But like I said, there can be other applications that have been identified and that are in fact used throughout the entire industry in which they are in fact applied. So let's have a look to the first application, which is the parity check bit. Parity check bits are used to verify if digital strings are sent from one application to the other and that they are correct. Now, the bit strings or the digital strings are typically represented in blocks of numbers, like I have here 0111, 0101, and we share them between computers and programs. Now, when we are sending a block of data, we add what we call a parity check bit, and we add it to each block of data that is sent. And the parity check bit will look into the correctness of the bit string that has been sent and that you received. Now, the goal is to verify what number of 1 bits you have in the string. And let's say the parity check bit will verify how many 1 bits you find in that string, and you can calculate it very simply by adding all the bits in the string and take the modulus 2. So when we have 0111, 0101, we have x1 equals 0, x2 is 1, and so on, and we take that sum modulus 2. So basically, the result xn plus 1 is 0 when we have an even number of 1 bits in the string, and xn plus 1 is 1 when there is an odd number of 1 bits in the string. Now, we can have an even number by adding two additional ones or adding two additional zeros. So basically, we can just only verify the parity, but there may be other errors in the system. So basically, you have to be careful because we have a verification that we received a bit string with an even number of 1 bits, or we received a bit string with an odd number of ones or 1 bits. Let's have an exercise. We have the different strings here. We have a string 1011 1011 0010, and we look at the string and we find 7 1 bits, 1 bit numbers, and it leads to the addition. We have 1 plus 0 plus 1 plus 1 plus 1 and so on, modulus 2. So basically we find 7 modulus 2, and 7 modulus 2, 3 times 2 plus 1, 1 is the remainder, so 7 modulus 2 is equal to 1. Now that's what we're going to do. We're going to add a final bit. That 1 bit is the parity check bit. Now let's have two strings here, 1011 and 1011, and 1001 and 1011. Now for the first one, we say, okay, the last bit is the parity check bit. So we look at the green numbers. The green numbers, 1 plus 1 plus 1, we find it's 5. It's modulus 2. So the parity check bit is 1, and we can say that the parity check is okay, so it is correct, and we accept this bit string to be correct. Now, like I said before, it's possible that we have a similar result when some other errors in the bit string occurred. So it doesn't mean that the bit string is 100% correct. We only know that the parity of the bit string is correct. Now we have the other string. We look at that. We have the parity check bit, which is equal to 1. So we say 4 modulus 2 is equal to 0 because it's even. So 4 is 2 times 2 plus 0 as the remainder. This means that the parity check bit is wrong, so there is something wrong with the bit, with the bit string, and we reject the bit string. So that's the principle of the parity check bit. Another element that we have relates to the universal product codes. We also call them UPC. Now you've already seen them, so we use them typically in retail products, and they are identified by standardized code. So you can find the country of origin in the bit string or in the string. You can find the producer. Every producer can have a specific code. Then you can have a code of the product. So when you enter the code, the UPC code, you may find out who produced the product, what is the description of the product. You can add information about the price and where it has been produced and information like that. So it's very interesting when it's standardized, and you can immediately see, oh, the Belgian chocolate, was it made in Belgium or was it made somewhere else? So basically, you can identify these elements. Now, the codes look like what we have here in the bottom. We have some codes here. We have the different formats, and typically there is let's say a relationship between the thickness of the lines and the number. So that we're not going to talk about that. We're just looking at how those codes look. We also call them GTIN codes, and typically what we find on goods we buy are the EAN 13 and the EAN 12 codes. So, the EAN 8 code. So we find both different codes. EAN 13 is used on larger packages, while the EAN 8 is used on smaller packages where we have less space to put the code there. But basically, it's a series of numbers, and we have to verify, is that series of numbers correct, yes or no? So basically, we have to find the check digit, and there are specific rules that apply. So when we look at the universal product codes and how we calculate the check digit, we use a formula, and in the formula we have different elements here. So we have the check digit. The last digit is in fact 10 minus the sum of all the numbers multiplied with a specific weight, modulus 10. Now n is equal to 12 or 7, depending if we have an EAN 12 or an EAN 8 code, which also means that when we look at the elements, we will see in the next slide what those weights are, because they are specific for this application. And we can say that the check digit is determined by the congruence of that sum plus the check digit is congruent 0 modulus 10. Now, what we're going to do here is, in fact, looking at the table. We're looking at a universal product code EAN 8. And the EAN 8 has the following format. So we have 2, 4, 3, 6, 7, 2, 5, x, and we want to find the check digit x8. So we put them from right to left, so we have 7, 6, 5, 4, 2, and 1. So basically here we could say that the last digit, the x, is basically x0, but typically we use x8. Now, what we are going to do now is to add the weights. And when the position is an odd position, the weight is 3. When the position is an even position, the weight is 1. So for 7, 5, 3, and 1, we have a weight which is equal to 3. And for 6, 4, and 2, we have a weight which is equal to 1. Then we multiply those. So we do 2 times 3 gives 6, 4 times 1, 4, and so on. So we find on the bottom line at this moment 6, 4, 9, 6, 21, 2, and 15. So basically what we have here, we take the sum, which is 63, and now when we look at the formula, so the x8 is 10 minus the amount here, which is 10 minus 63 modulus 10, which is in fact 7. So we find 7 as the check digit for this solution. 63 modulus 10 is 3, so 10 minus 3 is 7. Now we can now do this for an example with an EAN 13 code. So we have 12 numbers plus 1 check digit. So we have the same elements for both types of UPC codes. We set the weights to be 1 for the even digits and 3 to the odd digits. When we consider the EIN code that I want to consider, that I want to create, I have 2, 5, 6, 3, 6, 9, 7, 8, 4, 2, 3, 1, and then we have x as the last number, the number that we want to find. So we do the same principle here. We put them in the calculation. We multiply 2 with 1, 5 by 3, and so on. So all the even numbers are multiplied, or the numbers in the even positions are multiplied with 1, and the numbers in the odd position are multiplied with 3. When we add all of those, so we find for column 12, 2, then 15, 6, 9, 6, 27, 7, 24, 4, 6, 3, and 3, which gives us a total of 112. And when we put it in the formula, we find that this is equal to 7. So we have 112 modulus 10, which is 3, so 10 minus 112 modulus 10 is equal to 7. So that's the way we create an EAN 13 barcode. Now what we also may have to do is we have to verify the string using the check digit. is this string correct? Somebody sends us a string and we want to know, is it okay? We are not sure. So first of all, we verify if this EAN code is acceptable. So we have 12 numbers starting with 3, 7, 6, 2, 1, 1, 5, 6, 5, 3, 3, and 1. And the check digit is 5. So in total, we have, in fact, 13 numbers. We do the same calculation as before. So we multiply 3 with 1, 7 with 3, and so on. And we find the numbers, the results of the multiplication on the bottom row, and we add them. We find 83. You can do this exercise very easy. You can use any number and verify if it works. Of course, you can also find the calculators on the internet. There are a lot of calculators, free calculators that are offered. So you put in there the numbers, the 12 numbers or the 7 numbers when you consider an EAN 8, and you find the check digit. So when we put it in here, we find that based on this, on the numbers, the check digit should be equal to 7, and basically it says it's not equal to 5, so we can say that there is something wrong with the number. Either somebody put there the wrong check digit, or the other numbers are not correct. Anyway, we find out if the EIN is correct, yes or no. The last element that I want to discuss in this video is the International Standard Book Number, or ISBN. Now, books are identified with special designed book identification systems, or a book identification system, which is called the ISBN system. You can find all the information about the book when you know it, so you can put the ISBN number in the internet, in Google, and you can find the book. You can find all the information about the book in a very fast way. You find it on the book, so whenever people are using it in the points of sales, they click on it and they find the elements. Now, there are basically two types of ISBNs. There is the ISBN 10 and the ISBN 13 exists, but we will only consider in our exercise the ISBN 13, which we will calculate in the following slides. Now, when we have the ISBN 10, for example, we have 9 numbers plus a check digit, and that check digit is going from 0 to 9 and x. So we have 10 possibilities, and x represents, in fact, 10. So when we look at the ISBN 10, we look at the check digit, which we can calculate with a formula. X10 is the sum of index I times x index I modulus 11. So what we do, in fact, we take all the different positions and we multiply them with the coefficient y. And when we do this for this number, we find that x10 is congruent with 146 modulus 11, which means that it's equal to 3. So basically we add the last number, the 3, as being the check digit. So we can find the ISBN number. There are also the ISBN 13 numbers that are more used today because we have more possibilities to create different numbers for different books. And we know that there are different books that are, or more books that are produced over time. We also have all the digital publications, which also have special ISBN numbers. So that was it for this presentation, how we are going to apply, or how we can apply the congruences. We looked at the hashing function, we looked at the parity bits, we looked at the ISBN numbers, the UPC code. All these things have been considered. What we in fact learned in the previous videos, we can apply that. What we're going to do after finishing this chapter, because this was the last video, the last video of this paragraph. We didn't finish the chapter yet. So we are going to the next paragraph, and in the next paragraph, we will be using the congruences in cryptography. So finally, we will see how congruences play an important role in different types of cryptography. You're doing a great job. I'm looking forward to seeing you in the next video. Thank you, and bye-bye.